All right, here in this video I'm going to solve a rather complex problem for you that involves both a heating curve as well as energy transfer between two different substances. So this one is very tricky, so hopefully I'll be able to work you through the math so you can see what's happening. So you have 215 grams of very hot watery soup at 97.5 degrees Celsius. You want to cool it down to a reasonable temperature to eat. So you add 5.15 grams of ice that is at negative 5.25 degrees Celsius. And the question is, how hot is the soup after all of the energy is transferred? And then I give you some constants here. Let's really think about what's happening in this problem here. What's happening is the soup is cooling off. So since the soup is cooling off, the Q of the soup is negative. It is losing energy. The Q of the ice, on the other hand, is positive because it's gaining energy. We're transferring energy from the soup to the ice. All of the energy that the soup loses is equal but opposite in magnitude to the energy that the ice is gaining. So the negative Q of the soup equals the positive Q of the ice. We're going to need this equation again. I promise that I'm probably going to run out of room though, so let's just try to keep this in mind. All of the energy that the soup is losing is going into melting the ice. Now let's talk about that ice. This is not straightforward. This is not just Q equals MC delta T. The reason is that we're starting with ice at negative 5.25 degrees Celsius, which is a solid. It's going to undergo the phase change to become a liquid. Whenever a substance undergoes this phase change, it's not simple. So if we look and see what a heating curve would look like for the ice, remember the heating curve has temperature along this axis and energy added along this axis. We're going to start the ice here at our initial temperature of negative 5.25 degrees Celsius. It's going to increase in temperature as it's a solid until we get to 0 degrees Celsius. Then it's going to undergo the phase change to go from a solid to a liquid, and then it's going to increase in temperature until we get to the final temperature. So this has three different Qs. Ramps are Q equals MC delta T. Plateaus use stoichiometry, and in this case we would use the delta H of fusion because we're talking about solids to liquids. And then we have another ramp here that is Q equals MC delta T. So I'm going to label these Q1, that's the energy that it'll take to get the ice from negative 5.25 to 0. I'll label this Q2, that's the energy of the phase change, and I'll label this as Q3. The Q of the ice is equal to Q1 plus Q2 plus Q3. Okay, so let's focus on that ice first, and let's focus on these three Qs and see what we can understand and get from this ice part of the equation. So let's look at Q1. Q1 is a ramp. That means that it's MC equals delta T. So Q1 equals 5.15 grams of ice, that's the mass of ice that we have, times the specific heat capacity. We're a solid here, so the specific heat capacity we need is 2.11 joules per gram Kelvin or gram degree Celsius. Again, it doesn't matter because we're going to be dealing with a delta T. The delta T, we end Q1 at 0, that's the T final, minus negative 5.25, that's the T initial. So you can see all of our units are going to cancel except for joules. And of course this is addition of the opposite. So 5.15 times 2.11 times 5.25 gives us 57.05 joules. Let's look at our Q2 now. Q2 is on a plateau. A plateau is the phase change from solid to liquid for this particular compound. So we're going to use stoichiometry. We still have 5.15 grams. That's of water. The molar mass of water is 18.02 grams in every 1 mole. And then the delta H of fusion is 6.02. So every 1 mole of water requires 6.02 kilojoules of energy to melt it. Then I'm going to convert this into joules. Every 1 kilojoule is 1,000 joules. So 5.15 times 6.02 times 1,000 divided by 18.02 gives us 1,720 joules. That's what Q2 is equal to. Q3 then is our last ramp. Ramps are Q equals MC delta T. M is still 5.15 grams. The specific heat capacity, the phase we're in on this ramp is that we're a liquid. So we're going to use the specific heat capacity of liquid water, which is 4.184 joules per gram degree Kelvin or gram degree Celsius in this case. Doesn't matter because we're using a delta. T final, that's what we're looking for. We don't know what the T final is. After all of the energy is transferred from the soup to the ice, that's the final temperature of both. So the final temperature minus the initial temperature of this ramp is 0, because that's where the phase change occurred. So the initial temperature there is 0. So now 5.15 times 4.184 times T final gives us 21.55 T final. All right, let me get a little more room here. So Q of the ice is equal to 57.05 joules plus 1720 joules plus 21.55 T final. I'm just going to go ahead and collect these like terms. So we get 1777.05 plus 21.55 T final. So the Q of the ice is equal to 1777.05 plus 21.55 T final. This is still what we're trying to solve for. All right, so now let me go back up and show you what we're trying to do. The negative Q of the soup is equal to the positive Q of the ice. We figured out what the Q of the ice is. Now let's turn our attention to the Q of the soup. You have 215 grams of very hot water soup. I did that so that we could use the specific heat capacity of liquid water here as a close approximation for the specific heat capacity of soup. And it's initially at 97.5 degrees Celsius. So I'm going to do this part in blue. The Q of the soup is equal to the mass of the soup, 215 grams, times the specific heat capacity of the soup. And we're going to use that specific heat capacity of water to approximate it, times T final, that's what we're looking for, minus that initial temperature, 97.5 degrees Celsius. So the Q of the soup is equal to, this one gets a little complicated because we've got this T final in here. We're going to do your guys' favorite thing, 215 times 4.184, that equals 899.6 times T final minus 97.5. Your guys' favorite thing. We're going to distribute now. Very exciting. That distributes in. That distributes in. So the Q of the soup is equal to 899.6 degrees, or I'm sorry, 899.6 T final minus 87,711. So Q of the soup is equal to 899.6 T final minus 87,711. Again, look at what we decided already. Negative Q of the soup is equal to positive Q of the ice. We solve for the Q of the ice. We solve for the Q of the soup. Let's set them equal but opposite to each other. So, negative Q of the soup, negative 899.6 T final minus 87,711 equals positive Q of the ice, 17,705. Oh no, oh please, let me not make a typo here. 1777.05 plus 21.55 TF. Now we just have to solve for things. So once again, we're going to do your favorite thing in the world and distribute. Negative 899.6 TF plus 87,000. Oh, hold on a second. Oh yeah, plus 87,711 equals 1777.05 plus 21.55 TF. Add 899.6 TF to both sides. Subtract 1777.05 from both sides. $87,711 minus 1777.05 gives us 85,934. That then equals 21.55 plus, oh, hold on one second. I have a typo here in my notes. So let me just do this real quick on my calculator. 21.55 plus 899.6 gives us 921. Oh, where did I? Here we go. 921.1 TF. Just so you guys know what happened, I missed this decimal point when I was doing my notes up. So this number was way too large in my notes. So this is correct. 87,711 minus 1777.05 gives us about 85,934. That equals 899.6 plus 21.55 gives us 921.1. Now all we have to do is divide both sides by 921.1. Again, I have a typo, so let me just do that up on my calculator real quick. 85,934 divided by 921.1 gives us 93.3 degrees Celsius. And let's, again, I highly recommend that you do this. Go back and make sure that this makes sense. So again, what was the actual problem that we were trying to solve? We had a hot soup at 97.5 degrees. We added some ice to see if we could cool it down. And sure enough, we did. We cooled it down probably enough that I think this is still a little hot. I like my coffee around 87 degrees Celsius. So 93 is a little warm still. You might want to cool it off or blow on it a little bit. But that's how you would solve this problem. This problem looks very innocuous. There's not a whole lot of words. There's not a whole lot of stuff happening. But you can see that it's very complex. One of the most important things that you can do for yourself is anytime you have things changing phases is draw out one of your heat curves. That helps you distinguish between Q1, the temperature change, the solid going from negative 5.25 to 0, the plateau that uses stoichiometry for the phase change, and then another ramp where you get to your final temperature. The other most important thing from this, in my perspective, is to recognize the energy change. The soup is getting colder, so its Q is negative. It is losing energy. The ice is getting hotter, so it is gaining energy. So the negative Q of the soup is equal to the positive Q of the ice. That becomes unbelievably important down here. We need this negative sign here. If we don't have this negative sign here, then the math would never work out correctly. And so then there's your final answer. It cools the soup down to 93.3 degrees Celsius.